right, howdy y'all. Welcome to GeoClub. This is our 5th meeting. A very big thing. We're about halfway through the semester now, which is very fun class-wise.
Okay, so before we start this meeting, we are going to have a GeoClub Halloween cookout on the 29th of October. It's a Friday at 6 p.m. So if anyone has a phone and is thinking about going, I recommend you get out your phone and scan this QR code. It'll basically tell us that, hey, you want to go, and that means we're going to have food for you. It's just basically a hanging out sort of thing. We're going to have a pumpkin carving contest. We're going to have a costume contest. It'll be a lot of fun. We're going to be grilling a bunch of different things, and I suggest you show up. So if you want to take out your phone right now and scan this QR code, you should do it. And this QR code and the poster is seen on our social media. It's seen on our Facebook page, in the group chat, or group meeting. But yeah, here's our QR code. Here's our Halloween event. Make sure you know.
And we can always.
It is going to be at the ROC, at the front of the ROC. So, you know what? No, the opposite side. So you know where the benches are, the concrete is. Yeah, it's over there.
It's going to be on the water view side of the ROC,
Yeah,
the actual legitimate front.
Okay.
Yeah, and if anyone needs any slides, we could always pull them up after. Just talk to us. All right, so now we're going to introduce our speaker, the lovely Dr. Lumley, our head of department and a professor, and the Cecil and Ida Green chair in geophysics. Give me a quick second to share the screen. All right. There you go.
All right, thank you very much. All right, well, thanks for inviting me, and my talk is the future of Earth Sciences, which is a pretty big and nebulous title, and you can see there's a little asterisk there. And if you look at the footnote, it says, in my humble opinion. So obviously, I don't have any special powers to predict the future. But it is important right now, as I'll talk about, and it's particularly important to you all. But what's interesting right now, we got lots of changes going on in Earth Sciences and how that's related to society and the rest of the world, as I'll talk about in a moment. And so I constantly, particularly increasingly the last 5 years, get a lot of questions from students about, man, am I studying the right thing? You know, is there going to be jobs? Where are they going to be? Should I go to grad school? If so, what should I study? Things like that, because there's a lot of uncertainty and things going on that I'll talk about. Not only at that level, but also early and mid-career people, I have a pretty wide network, are also asking me the same question. Should I stay in my career? I've been working at X for 10 years. Should I be staying here, or should I try to move to something else? Then we have companies trying to figure this out too. Do we have, how much should we be investing in these various things? Because is it going to be there 20 years from now? A lot of times these investments, particularly in Earth Sciences, energy, minerals, whatever it is, are, 20-year cycle type investments. And then of course you have universities also trying to figure this out, because enrollments are changing rapidly. Our own department, we've had a lot of retirements. We're entering a rebuilding phase, and we want to know, well, what should we be rebuilding around? These are all really valid questions. I also serve on a few boards, and one of them is a Society of Exploration Geophysics. And our partners through AAPG, SPE, and AGU, I interact a lot with them. They're also trying to figure this out because they want to serve their membership. Memberships, the smallest of those societies might be 20,000 members worldwide to up to 100,000 members worldwide. And their demographics, their memberships are changing. They want to serve their members, but they don't know where things are going. And so we're in an interesting time right now where there's a real state of flux. And that's why I want to talk about it, because these questions are coming. So I have been thinking and talking and interacting with people for quite some time about it. So I'll just share my view of things. And of course, as good scientists, you would never just extrapolate from one data point. So you want to gather lots of data points to inform your own opinions and decisions about things. And mine is just one. So that's my disclaimer. All right, I'm going to show this movie for two reasons. Let's see if it's in the background still. Here, maybe. Can't see, of course. Let me go back. I know it should be.
It's gonna be one of those like
This
tabs at the
isn't-
very top, so we gotta get the top thing out of the way.
You find it, yeah, you want to take the top.
We also have to share the new screen, so I believe it was,
Just share the screen and chat.
there we go. I didn't realize that was an option.
Also, I think we should hide this.
Yeah,
Control,
Trying to,
Or, yeah, hide the at the top. Hide the floating meeting control.
Where?
The one in the middle.
Usually I display my movie in a separate window.
Are you trying to? Okay.
this one, correct?
Maybe, let's see.
Might have been the one before.
Yeah, it's right. It's backed up. We lost it.
Sorry
Here we go.
about that,
Here,
yeah.
that's okay. Everything's, you'll see my messages, keep calm, don't panic. About anything. Okay, watch. We don't need the sound. That's okay. I tried it before. It didn't work. Just watch this. So in part of my career, so I started in physics. And where I was studying physics, the specialty there was particle physics. And after a while, I was looking at thinking, I'm really bored with particle physics. This is just like billiards, playing pool on it with fancy equations. I wanted to do something more real world. I was also in some professional bands at the time, trying to decide, should I do that instead of do the school stuff? And ultimately, what I ended up doing to clear my head and make some money, I took a job on a seismic boat for a couple of years, and I worked my way up and ran the crew. And we were in several storms like this. This is not from my boat, it's from the internet, but I've been in many situations as good or worse than that. Let me just back that up and run it again one more time. You can see there's some pretty serious stuff going on here. And when you're on a boat like this and you're 300 miles offshore, it's a little bit scary, right? And you're wondering, are we all going to die? What the heck should we be doing? And for me, I was in charge of the seismic crew. I also want to protect people in the crew and their lives. And so what I learned through this kind of experiences is when you're in real big storms like this, the most important thing is don't panic. As soon as you panic and make a crazy decision, things are likely to go wrong. So stay calm, don't panic, and then make measured decisions about things and look at the big picture, because this storm is going to pass. It's not going to go forever. So you don't want to make hasty decisions and do wild and crazy things, because bad stuff will happen. So that's on the seismic boat. I learned that, and that has worked pretty well for life also. Now I've got to go back and find okay, you guys might have to help me here. Where the heck's our Zoom thing? PowerPoint? Yeah, but is this in the?
Yeah, it should be.
Okay. Oh boy, oh boy. Do this every day, but your setup's a little different from mine. Okay, so that's what I want to pass along, because we're in a storm right now, as far as I'm concerned, in our sciences. Don't panic, but you want to think about the bigger picture and the bigger picture forces, because that's going to govern where things go. So the storm in our sciences they're numerous. It's a perfect storm. Several things are coming together. We got intense pressures on the earth from society and everything we're doing as people. That's a huge change going on, to the point, as I'll talk about, it's not clear whether things are sustainable. That's one thing. The other thing is we're trying to switch, and it's related, switch from 100 years of certain energy supply, which has fueled our whole development in society. Everything we do today depends on fossil fuels, really. And it's not going to be easy to transition off that, but we know there has to be a transition. That's a perfect storm too. The other one is maybe around, we're taking earth sciences. If you kind of look back a couple of decades ago, the way earth sciences was being conducted is very field oriented, right? But now we're also having a data science revolution. It's impacting all fields of study. And so we've got to move. The field methods and so forth are core. They're not going to go away, but we also have to couple them with all the other advances in data science and computational science and things like that. And that's a big transition, in particular in fields that are not, it's not just earth sciences, but talking to people just this morning in biology and chemistry, they've got the same issues that, people are used to being in the lab and in chem lab making measurements, or, taking creek water samples in biology, and they've got to move into computational stuff. So we've got a whole lot of things going on that are causing a perfect storm. So, but that's okay. That's natural to change from one sort of period of stability and understanding to a new one, a new paradigm. But that's, I think, what's going on right now. So, so what the future is, if I wanted to boil it down to two things, and this is what we're trying to build rebuild our department around, is sustainable. So that's a really key word, sustainable, earth system science and natural resources. Both of those things being sustainable. Those are the two things I want to talk about today. I'll back them up. So first of all, what is sustainability? Well, there's actually, when you look out there, there's quite a few definitions. And I don't like any of them exactly. They don't quite fit. So I kind of cooked this one up from a few definitions. So my definition of sustainability is the ability of the biosphere, where we're living, and everything that goes into it. It's ability of the biosphere and human society to not only coexist, but to thrive together independently. And a good example I always think of in my mind, I come from a place where forestry and fishing was used to be the huge #1 resource, and is not anymore. And one thing I think that in North America, because we had pioneers coming here to a new land and we did things in a certain way, it's quite different than Europe, where people have been living there for many, many thousands of years. Of course, indigenous people have been living here for many thousands of years, and they were very good at sustainability. But anyway, forestry is one example. A non-sustainable forestry practice, and I come from the Pacific Northwest, is you cut down all the trees, clear cut them until they're gone, and then you move on to the next place. And that mentality was fine 50, 100 years ago because there were always infinitely many more trees. But now that's no longer true, and that doesn't work. And for that reason, tons of forestry jobs have been lost, and pulp mills, paper mills, everything in the Pacific Northwest. Europeans have a little bit different look at it because they realized centuries ago, no, we need to do this like farming. That's a sustainable way of thinking. We're going to just harvest enough trees. The harvest is what they call it, not cutting trees. We're going to harvest enough trees to keep this thing going, and we'll have maybe a farm, a forestry farm, that we're going to keep going for generations and generations to support our family for generations. We'll plant, we'll harvest, we'll keep it all in a sustainable balance. That's a really different way of thinking, and I think that just little example in my mind in forestry applies to lots of things. So sustainability, in my view, is the ability of the biosphere and human society to coexist and thrive together indefinitely. So this is a big deal right now, and everybody's talking about it at the corporate boardrooms, at government organizations, at professional societies, universities, everywhere is about sustainability. And one of the key areas you can go take a look at this is what's called the UN SDGs, Sustainable Development Goals. And I'm not kidding, this has come out of nowhere in the last 3 years, probably even 3 years ago, 5 years ago, nobody hardly ever heard about this or mentioned it. Now, everybody, you say UN SDGs, everybody knows exactly what you're talking about. So you should too, if you're not aware of it. And you can go to the UN website, you can just type in UN Sustainable Development. You'll see this chart and reports and versions of it on the website. You can see there are 17 of them. And I won't go through all of them right now, but a good half dozen, 6 or 7 of them, are all intimately related to earth science. So in other words, to meet these sustainable development goals relies critically on earth science. And that means, since everybody agrees, or most of the world agrees, this is important, that means earth science is going to be very important to ensuring this happens going forward. That means there are going to be jobs, careers, research funding, whatever it is you're interested in, teaching jobs, whatever in this area. So I encourage you to go take a look at those if you've never seen them or heard of them before. All right, so sustainable. So we talked about sustainability briefly. So let's first talk about sustainable Earth system science. So we know, but it's becoming increasingly apparent every year, every publication you see in AGU, GSA, wherever you see, we're learning things all the time about our Earth environment. And we know it's a complex coupled system between a bunch of spheres. So there's the geosphere, which is the solid Earth. There's the hydrosphere, which is the water. So that's the oceans. It also includes all the aquifers and so forth, water resources on land. Cryosphere is ice. That's a pretty new one in the last 5 to 10 years that's been added as its own sphere, so to speak, because all these things are coupled together with the water, what the Earth is doing, and the atmosphere, as we'll see. The biosphere, that's the portion where all life is happening. And it's coupled into these other ones. Critical zone, who's heard of that term? Just curious, critical zone. One. Critical zone is a few. Critical zone is a relatively new concept, but it's becoming huge and a ton of funding is being put into it. Critical zone is basically that zone on the Earth that life depends on. And it's loosely defined. It's not very well defined yet, but loosely defined, you can think of it as from the top of the tree canopy, tops of the trees to the roots. So let's say surface of the Earth plus or minus 100 meters, let's say. Now, other people say it extends a little bit farther than that, but basically it's everything, it's the realization that everything we need to live and survive comes from a very narrow zone. So we better understand everything that's going on in that zone, study it, and then of course, protect it or do something to make sure that we don't have a chaotic collapse of it. That's called critical zone, CZ. You often see it abbreviated as CZ, research, teaching, education. That is becoming huge. And then of course, coupled into the atmosphere, and everybody knows that. Everybody knows what's going on about climate change. Climate change is not as well understood, in my opinion, as a lot of people like to say it is. It's really complex because all these things are coupled together. But clearly, there's been a big realization that these coupled systems between the Earth, the hydrosphere, ice, glaciers, cryosphere, the atmosphere, etc. And actually, there's a growing realization those things are also coupled up to the ionosphere and even the magnetosphere. So we know, for example, in geophysics, we know the magnetic field is changing. The magnetic pole is moving very, very fast right now. And there's even discussion about whether we might be heading right now for a modern day magnetic reversal. The fact that the magnetic field is changing changes the influx of solar particles into the Earth. That affects the atmosphere, warming. I was just in a research talk on Wednesday afternoon, showing that in the due to the variations in the magnetosphere, I mean, on a daily or monthly or annual basis, can heat up parts of the atmosphere by +5 C. What do you think about that? Wow, those things. And a few years ago, we didn't even know, we didn't have the satellite data to show that kind of variation. So there's lots of interesting things going on right now that we need to learn more about. So that's a huge area, Earth system science, all these coupled complex systems, every one of them you can see has something to do, almost every one of them, depending on your definition, has something to do with Earth science. And they all do in my definition. So for example, in geophysics, we consider geophysics to go from the Earth through the atmosphere, ionosphere, planets, and beyond. And then when we get out of the solar system, maybe we'll hand it over to the astronomers. All right, so that's Earth system science. The other one is sustainable natural resources. And I know that you've heard things about this, but I'll tell you some more. What does that mean? So yes, it means forms of renewable energy, but not only that. And I have to say that sustainable involves, if we go back to that definition, yeah, what makes something sustainable? Well, we have to make sure whatever we're doing there is not impacting our Earth and environment in a way that can't go on forever, right? And so you see stuff now with renewable energy. We want to make a transition to renewable energy, but you also see recently people burying wind turbines and turbine blade in land dumps because they don't know what to do with the turbines after they wear out after 10 or 20 years. That is not sustainable practice to be burying massive wind turbines somewhere. For example, we cover a portion of the Earth with wind farms, solar panels. That's obviously going to affect the surface, the rainfall that hits on it, the ecosystem. So how are we impacting those things? That's a huge area of study that's really hasn't even started yet, that some of you, I'm pretty sure, will be involved in the future. So, we want to make this transition to renewable energy. Some people think that we can turn off fossil fuel energy. And again, you collect your data points, but I can tell you, having thought about this and been actively involved for a long time, there is no way we can do that because we've taken 100 years to build up this network and system of energy exploration, production, and delivering it to your home or your vehicle or wherever it's going, not to mention all the materials that are produced from that, plastics, synthetics, whatever, using it on something that has a huge profit margin, high profit driver to make that happen. There's no way we can turn around and in 10 years, you may have heard of net zero 2030. Anybody heard of that? Yeah. So we're saying in less than 10 years, net zero 2030, so in less than 10 years, we can make all our energy supply carbon neutral. So either take the CO2 that we produce from fossil fuels and re-inject it in the earth, or do something else with it, or plant trees as carbon offsets, whatever. There is just no way in the world we can scale up that transition. Right now, Texas is #1 in the US, in North America, for wind energy, and probably #2 in the world for a region. In addition to being #1 in fossil fuels. So Texas #1 in wind energy. Right now, talking to the wind power operators, they're kind of reaching an asymptote because they don't have, there are new places they could put wind farms, but they don't have a grid there, a power grid to take that energy and put it back into the system. And probably everybody knows, especially after February, we got serious issues with our power grid and all other infrastructure, not only in Texas, across the whole nation, because they're all 60 years or more old. So there's no way that we can scale up the amount needed to just overnight in 10 years. So instead, what we need to do is use fossil fuels as a transition energy. Think about it as a transition energy, but clean it up. And that involves CCS, and that's why there's a huge amount of CCS right now. And also new sources of energy are being developed. particularly nuclear sources and things like that from safer materials. These things, particularly the renewable, depend a lot on what are called critical minerals. So there are calculations that if we were to move completely to renewable energy sources, say, let's just say we want to get there, we need, in terms of critical minerals like lithium for batteries, selenium and other critical minerals that go into electronics to make that happen, we need at least, the conservative estimates are, we need at least 10 times more critical minerals than we know exist on Earth. In other words, we haven't found those yet to make that happen. That's another reason why we can't just overnight completely switch to these new forms. So right now, there's a lot of interest and money being invested in critical mineral exploration and development. Water, everybody knows water's a huge issue and becoming more and more of an issue, as we'll see. And agriculture and forestry in terms of optimizing our food growth with what we have and making it, again, sustainable. You might know, well, everybody's heard of Monsanto, I think. Everybody hates Monsanto. Because a lot of the production, the optimization in agriculture has been through chemical use and so forth. But now that's kind of coming back to bite us because where are those chemicals going? And there's people, everybody's heard of greenhouse gas CO2. Equally bad is nitrogen, NO2. And that there's a crisis in a nitrogen crisis, and because of fertilizers and how they go into the earth, the water, and into the atmosphere. Okay, so there's a recent report by the National Academy of Sciences, Science and Engineering, called Grand Challenges. It's coupled around engineering because it's applied science. But this report, it's a big report, but there's a compact version if you want to take a look at it. These are challenges identified that threaten our very survival, challenges to humanity, our survival. And they're so pressing, they say we need to put tons of research, investment, and jobs, and teach education and so forth into these areas. There's a dozen of them listed. They cover health too, science, engineering, health. These ones are directly related to earth science. So at least half of them, again, are directly related to science. Those are energy, as we briefly mentioned, critical minerals, regular minerals too, because we build things out of regular minerals, water, agriculture and food again, urban infrastructure. Now, how's that related to earth sciences? Well, you know, if we're going to build and completely smart cities, the next generation of infrastructure, that's coupled to the earth, obviously, and we need to know where to build things. A lot of stuff's going to go underground. How do we do that? We need to do a much better job at site characterization of the earth where all this infrastructure is going to be built, and monitor it over time. And there's lots of examples now of big projects that have gone completely sideways and even been abandoned after billions of dollar investment because they didn't do their basic homework on the piece of ground where that infrastructure was. If you're going to build a big bridge or whatever, a tunnel or whatever it is, a power grid through something, you got to know what is there and characterize it and then monitor it over time. All right, and then nuclear threats is also directly related to earth science through monitoring test bans, and even things like small dirty bombs. If somebody was to let off a small bomb in a city, where would the contaminant plume go? How would it flow through the city and the environments? So that just like fire is a similar thing. If there's a fire, now people are getting much more aware of major fire threats in some parts of the country. but where's it going to go? If a fire was let's say model it, right? If a fire started here and the prevalent wind conditions were like this, like they are this month, October, Santa Ana winds it through California where I lived for many years. You want to know how fast that's going to propagate, how long people have to get out. Do they have the road system to get out? A lot of these places, they don't, They left and they all got in a traffic jam in mountain roads and the fire swept right through them. Stuff like that. So there's a lot of earth science stuff. So energy, everybody wants secure energy. In other words, somebody else doesn't have it, we have it. Affordable, clean, and renewable. And this is often one of those deals where you get to pick 2 or 3 of these. You can't have all of them. Ideally, you'd like all. And so there are choices to be made. And again, as I said, fossil fuels are not going away anytime soon. But in terms of jobs, what is clearly happening right now, I would say, is that exploration for fossil fuels is being put on the back burner. And that's a huge change, because normally every year in energy companies, that's their biggest budget item, is their exploration, because they have to explore, find, and book reserves. That's a big part of the value of the company. Right now, what's going on is they don't know if we explore and find some energy reserves today, but it'll take 20 years to develop those. Will they be used or needed? And so they're moving huge investments off the table from exploration and focusing on production and monitoring and optimization and CCS. So a lot of those exploration jobs, there's going to be a lot less exploration jobs, but there'll be new jobs in production, monitoring, optimization, and CCS. So that's something to think about. It's interesting. It's happening right now. And it'll be increasingly thought of as a transition fuel, probably 1 generation, so 30 years, let's say. It's going to take 1 generation to go from where we are today, which is 85% of worldwide energy comes from fossil fuels, to some small amount, to tip the scales. Right now, just a few percent is renewable worldwide. Okay, continue developing these renewable energy sources, including all the materials and so forth that goes into it, but make them sustainable. Again, just because it's renewable, sun, wind, other things, geothermal, whatever, it doesn't necessarily mean it's a sustainable practice. And that's going to be important for earth science people. And new energy sources. Okay. So energy is one of the big challenges listed in that report. This comes from I've summarized from the engineering report, National Academy's report. Another one they actually clearly mention as a single challenge facing humanity on its own is CO2 sequestration. It's risen to such importance, it's actually listed as one of the dozen challenges. That, I personally have been working on CO2 sequestration for almost 30 years now, more than 20 years. But this is the first time I've ever seen it listed as a major threat to society's survival if we don't sort of get this right, get it happening on a bigger scale. Today, we have 20 commercial, did I include that? No. We have about 20, we've done about 150 demo projects of CCS worldwide over the past 20 years. We have 20 commercial scale projects, which means 1 million tons of CO2 injected per year for 20 years. So today we inject about 40 million tons of man-made CO2 into the earth per year to meet the IPCC requirements, and we're just 15% of the total geological sequestration, just a slice of it, 15%. To meet that, we need to scale up CCS by a factor of 250, even though we've been working up for 20 years. So 250 may or may not sound like a big number. So I usually say, imagine if you wanted to scale up your salary by 250. It's a challenge. So to get to some of these goals, it's going to take time, but a lot of money is going to be put into it. So what's earth science's role? CO2 storage exploration, exploring for sites to inject CO2 into, characterizing the site in terms of fluid flow properties, storage properties, mineralization properties, monitoring it over long periods of time. Right now, I'm on a circuit this year giving a keynote talk at all kinds of places around the world about we're going to be required to monitor these injection projects for up to 100 years. We don't know how to do that. We've never done that before. I'm almost 100 years old, but I haven't quite been monitoring things for 100 years. And then that's to meet regulatory compliance. There's a very recent report, 2020 IEA, CCUS and clean energy transitions, that describes this challenge very well. It's carbon capture, use, and storage. Used to be CCS, it's carbon capture and storage, but that's waste disposal. Take man-made CO2 and get rid of it somewhere, right? That's waste disposal. Nobody makes money from waste disposal. Nobody wants to do it. They always want to minimize the expense, right? And so, because it's not intrinsically worth anything. So, but the use part, we've been doing CO2 enhanced oil recovery or gas recovery and other uses for CO2 that are profitable. So we're trying right now to combine those two things to accelerate CCS, basically, so that there's a profit driver. All right, and CCUS is doing things like taking man-made CO2 from industrial sources like power plants, coal fire, oil fire, gas fire, power plants, cement factories. Does anybody know cement factories are one of the hugest CO2 emissions point sources? Nobody ever thinks about that. Agriculture sites, farms, and massive, huge CO2 generation of CO2. So all those kind of sites, and there are many of them, mineral processing, the idea is to capture the CO2 at the site, liquefy it, and inject it deep into the earth, deeper than a kilometer usually in a storage formation, and thereby accelerate the natural carbon cycle, speed it up by 1 million years. The natural cycle would be it goes in the atmosphere, dissolves in the ocean, precipitates in skeleton material, gets very compressed, et cetera, but that obviously takes millions of years. So do that, but also use it for something else. And this is a great plot I got out of the Wall Street Journal just a couple of weeks ago. So there is a global carbon market now. So you may know there's a global energy market. These are investment bankers and firms trading energy futures and stuff, all types of energy. There's also one pretty nascent for carbon, trading carbon. And look at the investment just the last few years in carbon market value. It's gone from about, let's say, 50 billion euros to 250 billion. It's exponentially increasing, and that is going to continue. What that means, that's a signal that investment bankers who have no personal interest or anything, they just want to make money, right? They're looking at this saying, this is going to happen, this is going to be big, a lot of money is going to be put into this, and we're going to invest in it now to try to make a lot of money from it. And that means there are going to be jobs and careers and things coming down the line, especially for earth science. Renewables, we already discussed. Critical minerals, we need 10 times, at least 10 times more than exists to make this transition, a full transition to renewable energy. Things like lithium, thorium. Thorium reactors are a really interesting thing that actually, instead of uranium, plutonium reactors, thorium reactors were worked on also back in the 1940s, and then they were abandoned. Thorium reactors are much safer, but they're abandoned because you cannot produce weapons from them. So they were abandoned. But now people are coming back and looking at that, and we have one of the first 1 or 2 commercial scale thorium reactors. But we need thorium and other critical minerals. Then we got to move the power around. We got to store power and move it around. So that's get back to our grid and so forth. Hydroelectric, fine. Hydrogen. Lots of people are talking about a hydrogen economy, right? Well, how do we generate the hydrogen? You need energy to generate hydrogen. Where's that energy coming from? And then once you generate hydrogen, where are you going to store it? And you know what people are talking about where it's going to be stored? They're going to inject it into gas storage reservoirs, okay? And then as they generate it, inject it there, and then draw on it as needed. Well, that's us, right? Earth sciences. You got to find storage reservoirs. You want to make sure they're not leaky, how to produce them, et cetera, geothermal, et cetera. So there's a big role for us to play here. Water, I'm not going to say too much about it because I think everybody knows, it's obvious, but basically it's getting worse and worse, or more and more urgent, to have clean drinking water for sanitation. Agriculture and industrial uses are huge, and we are running out of easily accessible water. Agriculture and food, as I mentioned, optimizing agricultural food growth, but maybe not doing it by chemicals as much, or with better, more sustainable chemicals. And here's this nitrogen, this report outline. Again, each one of these is a major challenge facing society. Nitrogen, N2O, is a greenhouse gas that nobody talks about. And it's just as big as an issue as CO2. It's a pollutant, it creates acid rain, it's a health risk being absorbed through water and minerals into young children, things like that. This report identifies it clear, it's a major crisis, nitrogen crisis, and nobody hardly is talking about it. Urban infrastructure, again, we've got our networks, distribution networks. How do we distribute fuels and energy around the country and around the world? Power, water, how do we distribute water and recycle water and things of that nature? Waste, we generate a ton of waste. Where's it all going? A lot of people don't know that there's lots and lots of everybody likes to hit the petroleum industry and they talk about wastewater wells. Well, that water is water that was produced from the subsurface, hypersaline, not produced, re-injected a lot of the time. But actually, there are lots and lots of people injecting wastewater from, let's say, chemicals, right? Dow Chemical, take them for example. Hopefully nobody works for Dow here. They got chemical factories. They're manufacturing tons and tons of chemicals, and there are byproducts and waste from those processes. Well, where do you think that goes? That's hazardous material. They can't just, what do you do with it? And so they mix it with water and they inject it deep in wells. There's a lot of stuff like that going on because it's a problem. They got a problem and how to deal with it, right? They can't just, old days, they used to dump it in the creek, right? And then the river would catch on fire. I think everybody's seen those videos. We don't want that, right? But they got to do something with it. So it's not exactly their fault because they are producing things that society wants that we don't want. But there are all these byproducts that we have to deal with. So there's lots and lots of things around these networks and grids. Natural disasters. We see extreme weather events and things, whether we can argue about whether this is a 100 period of time, there's no difference than, let's say, 10,000 years ago, maybe. Nevertheless, it's happening, stuff is happening, and we need to harden our infrastructure against it, particularly near shores, near the shoreline, near the coast. The US military quietly is spending more money, billions and billions of dollars, hardening all of their sites, bases, everything, because usually they're near the shore, hardening all those sites. They're not arguing about who's causing climate change or anything else. They're just like, this stuff is happening, and if we're going to have a viable defense, we got to make sure all our sites are functioning and protected from this stuff. Sea level rise, everything, extreme storms, tides. They're just doing it. So it's kind of interesting, quiet. I'm going to skip this one for now, but I mentioned the plume thing, which is really interesting. Predicting and monitoring how contaminant plumes, whether it's a large detonation, whether it's some terrorist bomb let off in a briefcase somewhere in the city, in some part of Dallas, where's that going to flow? How do you set up your warning system? And that's also directly related to things like pollens. I don't know who suffers from some kind of allergy from moving to Dallas. Never had an allergy until I moved here. But also how pollens flow or particulates flow in the air. That's a really interesting area, and it's generally part of earth science. The second report I just briefly want to mention, so all of that was applied, National Academy of Science, but it's about applied science and engineering. So those of you who are interested in applied science, that report will be very interesting to you, I think. Applied science jobs, earth science jobs. But the other side maybe is fundamental science. So there's also a lot of things going on in fundamental science and research. So these would be if you're interested in a career at USGS or a government research lab, a university, or maybe some Bechtel or something who knows a lot of, let's say, projects on the fundamental side. So this is the NSF Cores report. It's called Earth in Time. And I'm just going to show you the highlights of this. So what this report is basically setting out is the next 20 years of research and funding. These are the dozen areas where that funding is going to go in a big way. And that means if you're interested in the fundamental science side of earth science careers, this is where things are going to be. And so you might want to think about that to navigate your way forward. So how is the Earth's magnetic field generated? We still don't really know that, which is interesting. Of course, we have ideas, but we have shortages of data. This is a very active research project right now, putting up new satellites to try to measure it. First, you have to have data, right? That's the very first thing. And of course, as I said earlier, all these are coupled systems. So if we don't understand what's creating the magnetic dynamo, and we can't model or predict the geomagnetic field very well, then we can't predict how much solar particle influx is from the atmosphere and how that reacts with downwinds and everything else, right? It's all a coupled system. Okay, still, and Bob likes this one. How did plate tectonics start? That's still an open question, and there's going to be a lot of investment put in that. How are critical elements distributed in the earth? Well, that's interesting. That's critical minerals. That came up in the engineering report, the applied science report. It's also in the fundamental science report. That's pretty interesting when you think about it. You don't usually see things like minerals in NSF because that's usually not considered fundamental research or science. But the thing is, what's kind of going on is, just like people who might know about petroleum exploration, we have evolved a way of thinking about petroleum systems, right? Well, where's the organic material going? Does it get in the right pressure temperature window for the right amount of time, create hydrocarbons, then they have to have an integration pathway, a storage reservoir, a trap, etc. You have a whole systems way of viewing it. Minerals people do not really have that yet. They're just starting to, and Australians are in the lead on this, and a few Canadians. It's thinking of it as a systemic approach. How do minerals get deposited where they do? Not by, I would say right now it's sort of statistical sampling. Oh yeah, we find them here, we find them there, we map them, the GIS, we make correlations, things like that, but not exactly the whole systems. So there's some really interesting research going on right now. What is an earthquake? We still don't know exactly. We definitely cannot predict earthquakes, but we don't still really know all the mechanisms that create an earthquake. And I'm involved in a big initiative right now called SV4D, Subduction Zone 4D, space and time. And it's gearing up as part of this report, it's gearing up to be a major 10-year NSF research funded topic. To go out and deploy tons of instruments at subduction zone, both offshore, onshore. It's going to cover the earthquake mechanisms to understand those volcanoes associated with them, And then the geomorphology, how this, both the subsea surface and the surface responds to subduction zones. And that's coming and looking like it hasn't been created yet, but we've been spending 2 years of a big community gearing up for it. What drives volcanism? So, okay, that's a big one. Topographic change, understanding that better and understanding the linkages, again, all these coupled systems, how does changes in topography over geologic time affect things like climate change or migration of birds and animals, biosphere. Critical zone influence. That's the critical zone again that I talked about before, top of the trees to the bottom. And what does the Earth's past reveal about the dynamics of the climate system? Last three, how is the Earth's water cycle changing? That's a fundamental research question. Not only like the engineering applied science report, we want to know about hydrology and access, and aquifer recharge and things like that, but the larger cycles through these coupled spheres affecting the water cycle. Biogeochemical cycles. So here's getting back to these couplings between geological earth science things, biological systems, life, and chemical reactions and how those are coupled together. About 15 years ago, I was on a project, it was ground penetrating radar time-lapse project to monitor a Superfund site, a cleanup site. At this site, it's in Utah, it's an Air Force base. They were injecting water and producing water to recycle jet fuel. And this came from the 60s when they used to purposefully create fires to train people to put the fires out in case a plane crashed or things like that. And this was military base. And of course, that leach over the years leached NAPLs, jet fuel, into the subsurface. So they mapped it all out. They drilled a whole bunch of water injection wells to flush the stuff towards producing wells, clean it up, right? They figured it'd take 3 to 5 years to clean this up. 20 years later, they're still producing as much NAPLs as they ever were, and they have no idea where it's coming from. So we did a time-lapse ground penetrating radar survey. NAPLs are resistive, so that's what we're expecting to see. We noticed plumes in time-lapse data, plumes of conductive. And we're like, what the heck is going on? NAPLs are resistive. What are these conductives for? Finally, after talking to everybody we could think of, we realized microbes in the soil were eating the jet fuel, the hydrocarbons. And as a byproduct, it was changing the water chemistry, which changed the grains, the mineral grains, dissolving, precipitating, and we had conductivity. The water was getting a little more conductive because of these reactions through a biogeochemical reaction that none of us ever thought of or expected. So there's really interesting things to look at. Biodiversity, so that's directly related. And then geohazards, we've already talked about plenty of geohazards. So I think that's the last, oh shoot, I got 2 more slides to show you, sorry. One is where the jobs, and I think they are going to be in sustainable earth system science and or natural resources. Here are the projections from AGI, American Geoscience Institute, the current ones for the next 10 years. The overall growth in this is just for geoscience jobs, is predicted to be about 5% over the next 10 years. So never mind the doom and gloom sayers, the best predictions are there's going to be continued growth in geoscience jobs over the next 10 years. So that's good news, right? Because if everybody feels like, yeah, it's cratering, at least some people do. And some of those areas are 8 to 10% growth. And if you start looking at some of these higher growth areas, what have we got here? Environmental, geoscience engineering, environmental engineering, atmospheric and space, soil and plant, that's back to the agriculture and things like that. There is some growth, modest growth in geological and petroleum, conservation, mining and geological engineers, hydrology, interestingly, is just about 4%, some teaching, etc. So I think this is an interesting thing. If I was a student, I want to look at, make sure what I'm studying and training courses are geared to those areas. The second plot is not only where the growth's going to be, but what the salaries are, right? Okay, so the highest salaries tend to be in these kind of project management things in geoscience engineering, environmental and engineering. So what does that mean? The sweet spot for that is a master's degree in earth science, where you took 1 or 2 engineering courses, so you can kind of relate and apply your skills to something real, and some project management skills. So I would recommend everybody so first of all, if you're doing a bachelor's degree, those jobs are over here. Those kind of tend to be the technician and lab jobs at about $50K a year. If you've got a bachelor's degree and that's all you have, most likely in earth sciences, most likely that's the first entry level job. Field work, lab work, technician type work. But you upgrade to a master's, suddenly you're doubling or more your salary potential. But you also want to have a little bit of engineering and or project management business skills, because every team, no matter where government, no matter where you're working in as well as industry, there's going to be a team, and you're with your master's degree after a few years, you're going to be the team leader, the project leader, most likely to get paid those big bucks. And so you need to know how to manage people, resources, finances, and a project to make sure that it's completed and delivered on time. So that's essentially where those higher money jobs are. So I'll leave a copy of my slides, which you can send around if you want a PDF. You can look at those in more detail. And that's if we do have time for questions.
Have like 2 minutes or something.
2 minutes, okay, I'll answer one question and answer it really quickly.
Sorry.
No, that's my, okay, well, who's in charge here? You call on people.
Oh no. Let's go with Caroline, because that's our campus, I'll get you.
Okay. Caroline, is it?
Yeah, I just wanted to ask, can you like email us that PowerPoint or something? So a lot of that info is useful, like the graphs and the charts and everything.
Yeah, I'll send a PDF version of this, so you can all look at the numbers closely and see which salary you want to get.
And then we'll just review
Yes.
that based off.
So, I mean, I have a couple questions, but I have to talk to you privately about that.
Yeah,
Okay, so like, what is the process of like carbon sequestration monitoring? You know,
Right.
like, does someone just, sit out there and, whatever,
yeah.
like field site and just sit with kind of like a mud logging type, or?
Okay, so good question. So there's 2 aspects. You're kind of deep and then shallow monitoring. The deep monitoring is when we're injecting CO2, there's a plume spreading out over time. And we want to make sure, so it's mostly geophysical monitoring and some observation wells. What we're looking for is to make sure, is that CO2 going in the place we think we're putting it? And then how is it spreading out? If we want it to optimally fill the storage reservoir, we don't kind of want it to get stuck in one area and then, oh shoot, we have to drill another well to get stuff in over here, that kind of thing. So we're monitoring the plume as we inject. We want to make sure that because CO2 is buoyant, it rises. We want to make sure that our trap is really a trap.
Yeah.
The seal on top, whether it's a shale or something, or it's a strat seal. Then we want to make sure that the CO2 doesn't leak up any faults. So there's a lot of fault seal analysis that goes in ahead of time, predicting what the fluid flow properties of the faults are, but it needs to be monitored. So all these things we do a lot of work ahead of time. That's the characterization. But again, I use a comparison like if you get a paycheck and you put it in the bank, you put it in the bank, but you go check your bank account to make sure it's still there, right? So it's like CO2. We say we're injecting all this CO2. We know we are, but the regulator wants us to prove show us, show me the money. Show where the CO2 is going, how the plume is expanding. It's not, show me, it's not leaking up anything, which is not easy to do. And also we have a permit area that we can inject in. We must not cross the permit area because it's interfering with some other resources or somebody else's stuff. And so we want to see if it's getting close, like, oh shoot, it's racing ahead over there. We did not predict that. We're going to inject we're going to modify the injection profile. Quite often, it's not just a single CO2 well. Big project, it's multiple CO2 injection wells. Okay, that's down B. So it's a lot of geophysical monitoring and wellbore monitoring. There's also a up shallow aspect. So there's usually a environmental and kind of near surface analysis to get what the baseline conditions are, particularly with relation to natural CO2, because the earth is naturally, there are seeps from deep, plants generate CO2. The earth is breathing, inhaling and exhaling CO2 all the time from this boundary layer. So we need to capture that, study it ahead of time. So after we start injecting CO2, some farmer or somebody says, hey man, I got bubbles in my pond, right? And it's your project that's doing it, you know. So there's all that, there's a lot of geochemical stuff that goes into that, monitoring in the near surface and in the boundary layer, that in the air, but just maybe in the top tens of meters. We do a lot of aerial-based monitoring too, gases and things. Yeah, and there's been lawsuits actually in some of the big projects because somebody said, my cows are sick, or something happened. Our water supply is now Perrier, which should be more. You should get more money for that, but somebody's complaining, and there's a lawsuit, and have to go back to these studies to prove one way or another, you know, that this CO2 does not match the chemical makeup of the CO2 injected, you know, in the earth. Man-made CO2 versus natural types of CO2, but that varies from place to place. So you really, there's a lot of that near surface environmental type for science monitoring. Yeah.
All right, well, I hate to cut it off. Is there a preferred way of people contacting you if they have further questions?
You can find me online pretty easily. So the best way to contact me is to email me, and then and we'll go from there. But yeah.
Yeah, and we'll send out his email for that regards into our group me. So that anyone who wants to contact them and is in that group, then they can do so. But we're gonna pull back over to our way. Is that okay with you?
Sounds good. Yeah.
Awesome. Thank you, Dr. Lumley. Round of applause.
So we have a few more announcements. We have pizza waiting for y'all outside when the meeting's over. We're gonna do the mineral giveaway soon. Y'all feel free to get me drinks if y'all haven't already. Katie will take it from here.
Alrighty, so like we emphasize every single time, presents, we have had a lot more members, so we updated the picture. We're now at 44, which is a great thing. Our club is growing a lot more than the 14 that there used to be when we started this semester. So that's always nice. We like that. So,
as we've also previously told you guys before, this club is not just for us, it's for you guys as well. And one of the things that helps you guys is scholarships and internships. So this is one of the first scholarships that is available. It's the Max Glory Scholarship, where you get $1,000. The deadline for the scholarship is June 30th next year. That's June 30th, 2022. So if you want more information, this is the email, sorry, this is the website, and we'll also put this in our group meet and on our socials so you can apply. And then next scholarship would be this one. This is specifically targeted towards women, and it's for people who are interested in transportation or just generally engineering. So if you have any questions or if you want to see if you're eligible, I highly, highly encourage you to check this out at the website. And if you check your email, you should already have this because this was sent by our lovely professor. So please check it out. And they have tons of scholarships. This is just 3. I think they have like 6 or 10. Check it out, apply, and win 3 months. And as I mentioned before, we also have the internship. This is the LPI Summer Intern Program, and the deadline is December 13th, 2021. There are different requirements. It's open to everybody and anybody, but you may need some letters of recommendations, an application form, your transcript. So I highly, highly encourage you that if you are going to apply, you start now so you can get everything before the deadline. And again, this link will also be sent on all our socials so you can apply.
All right, so Fossil Mania. So this is an event coming up October 29th through 31st. We are going to be attending the 30th and 31st as we have our department party on the 29th. So we are looking for volunteers for this. We're hoping we get some strong people because we'll have to move some boxes full of minerals, which is a box of rocks. So they tend to be a little heavy sometimes. But it is going to be 2 days for us. So we're going the 30th and the 31st, and there is the opportunity to stay overnight with us. It's not a camping trip per se. It'll be a lot more like glamour, sort of like hotel experience at night. Not really that glamorous, but we're staying at a hotel. We're not doing tent camping. So if anyone is interested, please contact us or talk to us after the meeting.
Yes.
Yeah.
right, so-
We want to get kind of a head count of who's coming with us.
Yeah, we're gonna have to do that, especially if we're going to talk to SFC and get the papers straightened up for staying overnight.
On that note, if you do come with us, you do have to be registered, honor presence, like everything, because SOC is really fun about that. So we can submit the paperwork and that they can actually prove that you are a part of our club.
Yeah, I'm sorry, Kate. So, if y'all are interested in volunteering, please contact me. I'm Brittany. And for the overnight stay, if you are gonna stay in the hotel, we are asking that you help both days in order to be eligible to stay at the hotel with us. If not, we are also asking for 1 day volunteers. So if you can only show up 1 day or the other day, that's great too. So just let me know and we can work something out together.
Yeah, we understand it's a busy time of year for everyone, but we're trying to make it to where this counts as volunteer experience as well. We're trying to get registered with JSOM for this. We don't know if we'll be able to get registered this event specifically in time, but that is something we are working on for any people who are in JSOM who need the 100 volunteer hours.
All right, so as most of you probably know, we got a large shipment of new minerals that came in, generously donated by the Arkansas. I have some of them. We have tons of crates of geodes. And a little bit of an example. Yeah, we have 8 geodes here for sale on special, $10 each or $17 for 2. And we have plenty more downstairs, not necessarily for this price, but all really good prices. And I would love all of you to come down at some point and check it out. It's really cool. And I'm sure that you'll have your jaw hit the floor just like mine did when I saw everything.
We do ask that you do kind of try to schedule things with Blake because we have to stick a little bit more to these hours as there are PhD people working on dissertations in that lab currently. So we got to be respectful of that. So if a time doesn't work for you, please contact Blake and then we can get something sorted out for you. And then we can notify the people who are working in there to be able to, you know, see if they're okay with that time and if that works.
Oh, I have one last thing to say. Next week, I'm not going to be able to do the 5 to 6 p.m. on the 2 days, but the 2 on the 12 to noon and 1 to 3, I'll still be able to do. And after that, it'll just proceed as
All right, so last comes socials. So a lot of y'all know we announce a lot of things on Instagram, GroupMe, and Facebook. That's kind of our main points of contact. I do post meeting minutes on Presents still too, but we've already talked about that. And these are our QR codes as such, so y'all can get involved. The GroupMe is ideal for us because a lot of people do talk to each other about like random things as like, hey, I need camping poles, like my poles broke from my tent. I'm going camping this weekend if y'all can help me out. So like it's a lot more of a little bit more of a lax environment, but keep it geology based really.
And if any of you have a question for one of us or a question for one another, like Katie was saying, like say you have an idea of an event we could host or something, the main point of contact is group. You can either talk to the group as a whole or you can DM one of them.
We also have our emails listed on our Presence account, which is, you know, kind of like a point of contact that we sort of use, but we need to have people listed on there for SOC reasons. So we do post a little bit of stuff on there, but not really events as much as like, files that pertain to, GeoClub as the professional thing. All right, has everyone signed in? Because we are gonna do the mineral draw here soon. So if anyone hasn't signed in, the sign up sheet is right down there.
Right there.